While the photoelectric effect clearly suggested that the light sometimes can behave as a beam of particles, the other players in the effect, the electrons, were not really suspected to represent anything but particle-like entities. However, this latter picture was too questioned by a number of theorists back in the beginning of the last century, and notably by Prince Louis de Broglie, who suggested that massive particles can sometimes behave as waves. He was also a bit off in thinking that the photon also has a mass, but apart from this idea that didn't quite work out, his other hypothesis turned out to be correct. But it was actually serendipity that plays such an important role in physics sometimes that produced the clearest experimental results that confirmed de Broglie's hypothesis and put a nail in the coffin of classical physics. So let me tell you about this experiment and actually a rather curious story behind it. In April of 1925, these two gentlemen, Clinton Davison and Lester Germer, were working in a physics lab at the Bell Laboratories, and they were studying how electrons scatter off of a nickel target. They probably didn't expect any groundbreaking results when they started this experiment, and their initial results, as a matter of fact, were consistent with their sort of a boring expectation of a diffusive scattering of electrons off of the target. So here's the diagram of the paper, which shows from their original paper they eventually published in 1927, which shows the apparatus they used. So here we have this part, which is a gun, electron gun, which shoots electrons towards the target. And so this part is a nickel target they were studying. So another part of the apparatus is this detector, which detects electrons, and they can move it around, and by doing so they can study the angular distribution of the scattered electrons. However, what this diagram and the paper don't discuss and don't show is the full history of the event. Namely, the diagram doesn't show a bottle of liquid air that was sitting nearby and which exploded due to the heat coming from this target, presumably. And so this air, and it smashed the vacuum chamber surrounding this apparatus, and the air rushed into the chamber, heavily oxidizing the nickel target. So this was unpleasant by itself, perhaps, but it also made the target they were using completely useless for further experiments because it was completely oxidized. So Davison and Germer decided to save the target by heating it up and by annealing it to get rid of the oxide. So they did so and put it back into the chamber. And so they repeated their experiment with the new target, well, with the old target, but which had been annealed. But to their amazement, what they saw, the picture of the scattered electrons that they saw was completely different from the picture they had seen before the accident. But why did the results change? What was different? In trying to resolve this mystery, Davison and Germer examined the nickel target a little closer and concluded that heating it up, annealing it, resulted in its transformation from a polycrystalline form, which basically implies a number of small crystals put together in a random fashion, to a few single crystals with a perfect crystalline order inside. So, and this eventually explained the new results. But what are those new results? So instead of a random blob of scattered electrons, they now saw clear peaks corresponding to the electron beams reflected from the crystal at certain specific angles. And these angles were strongly dependent on the energy of incoming electrons. So this plot here is actually the plot from the original paper by Davison and Germer, and it shows so-called scattering curves for what they call the 54 volt and 65 volt electron beam. Those numbers refer to the energy of electrons. Perhaps a more illuminating modern picture of the same phenomenon they discovered is, of course, a different experiment, but maybe different material, but the same phenomenon, now known as electron diffraction, is presented here. And so what is remarkable here is that this time phenomenon is something that only waves can exhibit. upon propagation through a regular array of scatterers. So these bright spots here correspond to the directions along which the intensity of the scattered electron beam is high. And so this phenomenon is known, and here is a reminder of this picture. So if we send a wave towards a crystal, depending on the angle, the reflected waves from different layers, they can either enhance each other if they appear in phase, or they can appear out of phase, in which case they will cancel each other out, and this will correspond to sort of dark regions in this plot. And well, this had been known before Davison and Germer's experiment, and they readily recognized it and found that their data made perfect sense if the de Broglie hypothesis were to be accepted. And so they actually say in their paper explicitly, here's a quote from the paper, the most striking characteristic of these beams is a one-to-one correspondence which the strongest of them bear to the beams that would be found issuing from the same crystal if the incident beam were a beam of X-rays. So they're saying if they were to scatter X-rays of the same crystals, they would show the same picture. And finally, they say so their data made sense if it involves association of a wavelength with the incident electron beam, and this wavelength turns out to be in acceptable agreement with the value of h over mv, h being the Planck's action constant divided by the momentum of the electron. So this was a rather remarkable verification of Prince de Broglie ideas, and the main equation, which again is this equation, which relates the properties of a particle with a mass moving with a certain velocity to a wave that would be associated with this particle. And these ideas brought him a Nobel Prize just 4 years later. So to summarize, let me just tell you what we've learned so far in the last two segments. So far in the first lecture, we have talked about two Nobel Prize winning works, the photoelectric effect and electron diffraction. And all in all, we met in passing at least 6 Nobel laureates in our first lecture: Feynman, Michelson, Lenard, Einstein, Davison, de Broglie, so not too bad. And we have seen, and these are basically the main conclusions from the two experiments we just discussed, we have seen that there is a clear experimental evidence that light behaves sometimes as a beam of particles carrying energy quanta, and the frequency relates to the energy as so, or the wavelength of light relates to the energy according to this expression, where the coefficient of proportionality is the Planck constant. So here omega is the frequency of light, c is the speed of light, and lambda is the wavelength. So on the other hand, there is also evidence that electrons, massive particles, sometimes behave as waves. And the relation we just discussed, it is de Broglie relations. And in the next lecture, we'll try to figure out what is going on here.